Okay, in today's lecture, we're going to be talking about databases, specifically relational databases, and also talking or introducing SQL or the structured query language. So we're going to just do a quick introduction of this, and then we're going to do some hands-on coding, as I would say, with SQL and interacting with a database. All right. So there are two different types of databases. There's relational databases and non-relational databases. On the left over here, we have a relational database, and you can see there's these little boxes or what are actually called tables. And these are these little lines. This is just like a visual representation of a relational database. Where on the right-hand side, this is a visual representation of a non-relational database. There's nothing that's really, it's very kind of difficult to relate specific data in here with other parts of the database or other parts of the data or other pieces of data that are stored in the non-relational database. At Platoon, we're focusing on relational databases, specifically Postgres. There's about 10 years ago, late 2000s, early 2010s, there was a big push to using non-relational databases. They got really popular, but since the past probably 5 to 7 years, the kind of pendulum swung backwards to relational databases because relational databases there is just it's just easier to work. I don't know necessarily it's easier to work with, but there's a lot of benefits for working with relational databases. So there's two halves to a relational database management system. So that's what RDBMS is. So relational database management system. There's the storage mechanism, as in like how to manage the data, how to store the data. And we're going to talk about specifically how we store data in relational databases using tables. There's these things called tables and columns and rows. And also the querying mechanism. So the language that we're going to be using to actually query the database to get data back or send data to the database. So yeah. So there are these things called tables for our storage mechanism. So here is an example of a table. So this whole entire thing is a table. It's specifically called the students table. So each table has a name, and this specific table is an example called students. And each table has a column, so or multiple, at least one column, probably at least two, probably in reality like 3 columns at least. So there's columns, and these columns are unique fields of the type of data that's going to be stored. So here's an ID, ID1, ID2. We have first name, Tiana, Elda, last name, low, snipes, operation, false, true. So each table is columns. In addition, each table also has rows. So these rows are unique data that's input into the database. So these should be unique. There shouldn't be duplicates in this, like there shouldn't be 2 Tiana low falses with an ID of 1 inside the student's table. So let's talk about schema. So we kind of talked about an individual table, what it consists of. It consists of columns, rows. All the tables also have headers. This looks exactly kind of like if you've worked in Excel or Google Sheets, it looks almost, you can like kind of, if you envision a table as a sheet in Excel or a sheet in Google Sheets, and that has headers, and in each row is a unique piece of data. Now we have a schema. A schema is essentially the entire plan or blueprint of how the database should look. Like how you're going to store, how many tables you're going to have, the names of the tables, how many columns each table is going to have, the headers of each table, and just also the different types of data that should be stored in each unique column. So if you come back here, ID consists of numbers, first names consist of text, and on the probation column consists of like a Boolean value. So we can verify that when data is going into the database, that the specific data types going into these fields are in fact the correct data type. That's where we come into data integrity. So again, primarily focused on describing three things: table names, and column types. So example, column names, first name, column type. This would be a text field or or like integer field. And then also the name of the table, which is students. Other parts of the schema include whether or not a column must have a value. So null versus not null, foreign keys, indexes, etc. We'll get to that later on in later lectures. So for example, what if, I don't know, like if there's another like middle name column in here in between first name and last name, and middle name column was optional. So it didn't necessarily always have to have a value in there. So it could be Tiana null or like no value and last name. So it can be like an optional column. So tables are identified by name. So just like if we went back here, this is the students table. And so this is right here is in fact a SQL query. Create table students followed by, the number of columns, the types of data that need to go in each column. So this is an actual SQL query right here, and we'll get into what that looks like. Here's another one: create table addresses. So this is how we create a table in our database, and we'll get into actually creating a database in our command line a little bit later. So create table addresses followed by some other information, but the main query is create table addresses followed by the table name, parentheses, and also an ending parentheses at the end. A lot of people forget that, and it'll throw an error. Well, almost any name is valid. These are good naming conventions to follow. So generally speaking, all table names should be lowercase and plural noun. It's also very good practice to include a unique integer column named ID on every table you create. So if you look over here, students, so the students table stores multiple students. That's why it's plural. Also, it has a unique column called ID, which has unique IDs for each data entry in the students table. So it'd be 1, 2, 3, 4, 5, and you'll never have multiple, or you should never have multiple IDs of 1 or 2. Each row should be unique. Even if you delete, if data gets deleted, you won't replace an ID. It's just that ID is done or it's nullified. So you'll never have a duplicate or replace. Generally speaking, you'll never replace it with brand new data. So I'll never replace the ID of 1 with brand new data. So table name examples, here are some examples. So think about what the data in the table stores. So again, a database has at least one to many different tables. Each table, it should be named similar to what it actually stores. So like a noun. So for example, if the table stores people, the table name should be persons or users or something like that, or students. So if you are working at Amazon, or if you start a small online company that allows customers to buy specific items, you might have a purchase order table. So you'd have purchase orders. Or if you're working at Facebook or Twitter, you might have, when you can like a post, you might have a table called column, or a table called likes or impressions or something similar to that. So we have a likes table. So we talked about tables. Now let's talk about columns. So each column has a name. Lowercase singular nouns or adjectives are a good naming convention. So just like we had up back here, ID, first name, last name, on probation. If we go to see what that actual query looks like when we're creating a table, so we're create table students, we have an ID, which is an integer, first name with a space, varchar, so a varying character or something like that, with a length, a max length of 255 characters, a last name, column name, the data type is a varchar, it has 255 character length, and then we have an on probation column with a Boolean value. These varchars, that is basic or standard SQL convention. So you can have varchar, integers, Booleans, dates. There's a bunch of different ones, but varchar is very, very common. So let's see. So now we get into column types. That's what we were just kind of talking about. So each column type has a type which determines what kind of data it can hold. So a varchar or a text, that's essentially what that is a string. So varchar is a string. Boolean is, you know, true or false value. Integer is a number. So varchar is a fancy way of saying a string up to 255 characters long right here. So when you go ahead and try to insert data into the students table and say you have a first name and you somehow type in some numbers and it tries to save in the database, it'll throw an error because it'll say like, hey, that number that you tried to put in the place of first name is not a string. So it's going to throw an error and be like, hey, you can't do that. It's all about data integrity in your database, because once if data is stored in your database in a specific data type that isn't good representation for that data, you might have to go back and change it. It's very cumbersome to go back and change all the data entry, all the data entries in a specific table, trying to change all the types and everything. So we get column types. Here are just examples of specific column types. Different database management systems or relational database management systems all pretty much have the same types, but just maybe a different flavor of SQL. So integer, decimal, varchar, text, date, timestamp. These are all standard like SQL commands or SQL types, SQL column types. So you may have heard of like Postgres, MySQL, MS SQL, Oracle. These are all different relational database management system, but they all pretty much use the same flavor of SQL. Schema modification. So as your application grows, you might have to modify your database to account for the growth of your organization. So for example, Amazon, Amazon started up as a bookstore. So they may have just had like a users column and maybe even like a users table and maybe a books table. Obviously they probably had many more, but they only sold books initially. And as Amazon grew to selling DVDs, they may have just aggregated all that into like a products table, or as they grew and started using Amazon Alexa, they might have different tables to support that. Or if they, just all the different plethora of products as AWS grew, they might have had to create tables for that. So as you maintain software, it's especially that you'll create new classes, write new methods, and refactor existing code. You'll do the same for your database. So new features often require new tables and columns, or perhaps migrating existing data to new schema. I know at my last job, as we added new features and just capabilities of our product, we would modify specific columns in already existing tables or add new columns to tables. So we just be aware that schema modification, modifying your database as it grows, is common. So existing columns can also be modified to hold new types of data. And if that's the case, you'd have to like run a script on all, like a script on your database that change all of the types in each column, or in each column. So so changing a database schema often isn't cheap either. It can often require coordination with code changes, etc. That's why it's very important. Just like when you're pseudocoding a technical challenge, you want to make sure it's right the first time. So as you're writing it, you don't have to go back and modify it later on. So take your time when designing your database schema. So when you're designing all the different tables and how they relate to one another. So just take your time, because you're going to find, especially starting out, that you're going to be dropping your database or deleting your database and starting fresh, because it's just easier initially because you don't have a whole lot of data in it. But when your database is growing and you're working in a company and you're working in like a production environment, you can't just delete your database and start over, because you're going to lose all that data. So make sure when designing your database, do it right the first time. Take out a piece of paper that's kind of like pseudocoding. There's plenty of tools online that helps you pseudocode or design your database schema. All right, single responsibility. Just like we write our functions and classes to be as slim as possible, or how we want to break up our functions to have into like a little more modular, so the functions or classes or methods are slim and they only do one thing and do that one thing well. We also want our database to do the same. So we want our tables to be slim and just specifically hold the data that table specifically is supposed to hold. So we don't want to bombard a single table with all this other data that it doesn't need. So instead of having one table with 100 columns long, with all this different data, that's it could be users, it can be addresses, it can be grades, it can be anything. We want to break up that single table into much smaller tables, where each table is only responsible for storing a very specific piece of data. So again, here is a quick example. So here we have a students table. It could be this was our students table, and we have our first name, last name, on probation, and then we also have their address, line 1, line 2, which is optional, line city, state, zip code. So this might seem not that big of a table, and it's really not that big of a table, but we want our tables to be single responsibilities, to only hold the specific data that we want. And in this table, there's two distinct pieces of data that we have in here that are combined into one table. We have our student, which we have like first name, last name, on probation. We also have our address here. Those are two distinct different pieces of data that we have in this single table. So what we'll want to do, like, and it's okay if it's like this on a small scale, but as your database grows or as your users grow, you'll want to split these up into multiple tables. So we have our students table and we have our addresses table. But now you get into the issue of, well, okay, if Tiana lives at 381 Maple Street in Chicago, how does the address table, how do we associate this address with this student? And that's a very common issue. And this is where the relational databases are useful. So don't repeat yourself. So, but we'll get into how these two tables relate to one another. But we'll also want to talk about don't repeat yourself. Just like we do in code, dry programming, we also want our databases to be dry. So we don't want two pieces of data to be two pieces of the same data to be in two different tables. So yeah. So right here, an example. If we broke off the students table into the addresses table, we have first name, Tiana, low, false, probation. And then in the addresses table, we also have Tiana and the last name in here. So this is bad design because we have two different pieces of data. So Tiana and low in two different pieces or two different tables. Yeah, so this is not ideal. So, because what if somehow, Tiana changes her first name and it updates in this table, but for whatever reason, it doesn't update in this table, in the addresses table. So that's not good. It just leads to errors in your application. So what we can do is, so there's a duplication right there, and we want to get rid of the first name and last name in the addresses table. So with this duplication, what are the downsides we can expect if a student changes their name? Again, it might change in the students table, but it might not change in the addresses table. So we can fix that by keeping our code dry by using what is called a foreign key. So inside the students table, we add another column called address ID, and we associate essentially the value of this address ID will be associated with the ID in the addresses table. So Tiana, first name, last name, false. We have an address ID. We can do a query that also brings in the address table to look for where address ID equals 4. And there we go. We're able to get Tiana's address through the students table and the addresses table. This is what it's called like a join table. We're joining two tables together, and we can extract all of Tiana's information through this join table. So address ID 4, coming down here, addresses ID column is 4. There we can grab her addresses there. So data integrity. Good schema design improves your data integrity. So just like we had specific data types for each column, we also might want to have some checks in there where you can't have duplicate values or values in the same field or in the same column. So we have two examples. Here's an example. There's two people that somehow stores two different email or two of the same email addresses, james@example.com, an ID of 2 or column 2. I'm sorry, row 2, and james@example.com in row 3. So when you go into login, say my email address is james@example.com, I go onto the website, I log in with my email and password, type in james@example.com, I type in my password. How does the application know what field or what piece of data to look at? So this is where it's like, oh, you should have some checks in your database, or as it's saving data into the database that says, okay, you can't have another email address in the email inside the users with the same email address. So you can have making sure that this is unique in the database. So careful use of database constraints such as column uniqueness or not null will protect you from situations like this. So which password should you check when James logs in? Doesn't know. And this password right here, this is called a hashed password. So you never want to store passwords, like the actual value of your password in the database. You'll want to run it through a hash that hashes it, and it stores it like this, so you can't decipher it. If someone were to hack into your database, and try to steal all the passwords. They would just see this and they would have to decipher this hash in order to get your actual password. Never write your, so there's plenty of libraries out there that already have this capability. So use an already existing one. Don't create your own, just for future reference. So queries. So we talked about, creating a table. Now we're going to be talking about queries, actually grabbing data from the database, inserting data into the database, and updating data in the database and deleting data in the database. So in SQL, all types of commands are lumped together and called queries. So a SQL query, including commands that don't necessarily query for anything, but instead do something. So create table, like I just mentioned, is a query. So we're querying the database by creating a table. But most often you'll be querying a table with the following commands: select, insert, update, delete. So select is you're retrieving rows that match a specific query. Inserting, we're obviously inserting new data or inserting rows. Update, we're changing rows that match a specific query. And delete is where we're going to be deleting a row that matches a specific query. So here's an example of the select keyword. So right here, you'll say select star. So this star means select everything from the students table and return it. So if we do select star from students in our existing students table, it's just going to return Tiana, like ID, Tiana, low. So it's going to return those two rows. So these don't have to be uppercase. This is just how this person wrote it, but this also can be lowercase, like lowercase select, lowercase from students, but you definitely need the semicolon at the end. So this is the most common one you'll see. You'll be using this all the time. And then, so this select star from students, that selects everything from the students table. Now, if we're doing, now we can select very specific columns from the students table by doing like select ID, comma, first name from students. So that just returns the ID and the first name from the students table. Often you want to retrieve only records that match a specific condition. So instead of returning everything from like the students table, maybe we want to find the student where the student with first name of Tiana, or where an ID, the student's ID equals 2. So here we'll want to select the ID and the first name from the students table where, so that there's this where condition, where the ID equals 2. So if we do that, we just return the ID and first name where the ID of the student equals 2, which is ID is 2, first name is Elda. So the where condition, so where are numerous conditions supported by the where clause? Here are a few. So the equals is the most common one. You also have not equals, or not equal to a value, greater than, less than, values, between. So a column or a query can be between two values. The in column is represented in a list of values. So if you return something, is it in a list of values? Or like matches a string with wildcards. There's like, there's I like. So yeah. So if I wanted to return a first name that has a J in their, or I want to return all users that has a J in their first name, I might use like. So here are some examples. So selects everything from the students table. So select all the students in the students table where the first name equals Andre. So I would just literally return all this first query would literally return all the students in the students table where their first name is Andre. So the second query is select everything from the enrollments table. So for example, we might have an enrollments table for students, or in a school, for such as like school interface challenge. We might have an enrollments table where the grade is in between not equal to an A. And then select everything from the classes table where credits are between 3 and 4. So maybe you enroll in a university, each university has maybe a classes table that has a list of all the classes and also a credits column where the number of credits for those classes. So this would return all the classes where the credits for those classes are between 3 and 4. And select star from enrollments where grade is in A or B. This last one, this is that wild card. So select everything from the classes where the name, so the column name, and we have this art with a percentage sign. So this percentage sign is essentially saying we want all the classes where the first 3 characters of the class is art followed by anything else. So this would literally return all the classes that start with the word art. And it doesn't matter what is after that. Also, we can add if this and credits is greater than 3. So we can do ands, keep on adding multiple conditions onto one another. So select all the classes where all the classes where the name starts with an art and where that art class has credits greater than 3. Insert records. So insert inserts new data into, so essentially new rows into the table. So we can say insert into, so insert into the students table, and this is where placement matters. So first name, last name, birth date. So the column names, first name, last name, birth date, the values of Michael DuPont and the birth date, 1982, 02, 11. So if we switch these last name and first name, then the person's last name would be Michelle and their first name would be DuPont. So we have to make sure the order is correct. Updates allow you to change the values of a column. The new column is applied to all rows that match that where condition. This is kind of dangerous because if you don't include this where condition, it'll update everything in the addresses table. So update in the addresses table, we're going to set the column line 1 to equal 200 Church Street, as well as the zip code column to equal 60010, where the ID equals 2. So wherever the ID equals 2, we're going to update the line 1 column as well as the zip code column. It's dangerous because if we don't include this where column, it'll literally just update every single field or every single column, line 1 and zip code with this value, which is not good. So you always want to include a where condition. And deleting removes matches rows from a column or from a table. So delete from the addresses table where ID equals 2. It's pretty straightforward. Update and delete without conditions. I think I just mentioned this. Caution, if you fail to include a where condition, you'll affect all the rows in the table. So everyone moves to that 200 Church Street if you do not include that where condition. And if you do say delete from addresses, you'll just delete all the addresses in the table, which is never good. And there's no way to get it back. No easy way to get it back. You can't just do Control or Command Z and have it be undone. All right. Okay, we just went through an intro to SQL. Now let's actually do some coding within SQL. So I'm in here in an intro to SQL directory. There's no files in here yet. So I can directly access a database or even create a database from the command line. If you installed Postgres correctly on install-fest day 1, you should have your Postgres server running. If it's not running, that's okay. We'll help you. But here we go. So in order for me to create a database, so let's actually create a database called November Platoon. So I'm going to create a database in the terminal. So I'm just going to zoom in a little bit more. There we go. Called create. So this is an actual command, create DB, which stands for create database. I'm going to say November Platoon. Platoon. If I click enter and nothing happens, that's usually a good sign. Now I can determine, I can see whether or not this database exists by running PSQL, which stands for like Postgres QL, followed by the name of my database, November Platoon. And now it says November Platoon with a little hash. Now I'm literally in my database and I can run queries from here. So I can literally say like select star from some table. And it says error relation some table does not exist. Cool. So I just created a database. I didn't create any tables in my database yet. So I can actually create a table. I could do it two ways. I can do it in here. I can run create table students, and do that whole thing, like do a bunch of stuff. I'm gonna clear that. I just wanted to exit out. Come back in here, or I can create a file, which is a little bit better, to create my database schema. So I'm going to quit here. So I can do \Q and I'm going to clear the screen. And now I'm going to create a file called schema. So touch schema dot, and this is not a Python file. This is not a JavaScript file. It's not a JSON file or text file. This is a SQL file. So I'm going to do SQL. So schema.sql will create a SQL file. If I click that, there, I've got my schema.sql file. And notice how the icon is like a bunch of yellow disks. That's what kind of like a database is. So if I open that up, and if I so I open this up and now it's empty. Now if I go back to the slides to create a new table, we can look at the query create table students followed by this. I'm actually going to scroll down here. So if I did something like this, I can create a table using like a query like that. So I'm just going to say create. I'm going to do everything in uppercase just to keep things. Create table. Create table, and notice how the create table turned blue because it knows that, hey, this is in fact a SQL query. I'm going to create table students because this is going to be a students table. I'm going to do open parentheses followed by a closing parentheses. Now I'm going to do ID, and this is going to be unique. I can do integer like so, but I'm going to, in the documentation, I want this to be the primary key. So anytime in the Postgres database, anytime you insert into a new piece of data into a table, I want this ID to be automatically added and increment by 1. So don't worry if you don't know what this is yet. We'll cover this later. So serial, and this is going to be a primary key. So this is the primary key of the table. So this ID is going to be unique every single time. And it's going to serial, means it's going to increment by 1 every time I input a new piece of data into this table. So I'm going to say first name. First name is going to be a varchar with a maximum character length of 255 characters. And I'm going to make this a not null. So this always has to have a value in it. So if I try to insert some data in there, it won't work. And I'm going to do last name. I'm going to also do varchar 255. I also want this one to be a not null. So I can literally run this in here by just copying, pasting that, and running it. And notice how nothing happened. But now, actually, yeah. Now if I just do, disregard, I'm going to quit there. I didn't, why not? Create table students. Let me back up. So before I run that directly in the command, I'm just going to actually run it directly into I'm going to run this file in our SQL database. So if I run PSQL, so hold on, let me list everything out. Schema, there's my schema file. It consists of create table students with an ID, first name, and last name. So I'm going to run PSQL. So inside the November Platoon database, I want to insert, so little angle bracket, the schema SQL file. And notice how it said create table. That means it successfully created a table. If I did any of this wrong, it would immediately throw an error. So I'm gonna actually, so I created a table. I can also drop a table. So I'm just gonna, before I do that, I just wanna see something. Okay, so inside my November Platoon database right here, I did \D, which will return a list of relations, essentially a list of tables. So it's got the student table right here. It's a type of table. And this student's ID sequence, just I believe it means that, I could be wrong, and that table is has a sequence ID in it. But you don't really need to know about this one. So I'm going to quit there. I'm going to clear the screen. So I created a database. I just want to show you how to drop a database as well. So to create a database, it's create DB followed by the database name. In order to drop a database or delete a database, you could do drop DB followed by the name of the database. And notice nothing happened. And now if I try to go into the November Platoon database, it says PSQL error failed, database November Platoon does not exist. So I'm going to clear it. But let's go back and recreate our database, create this table, and add some data to it. So if I go up, I can do PSQL. Keep going up. Create database November Platoon. Cool, worked. Now if I do PSQL November Platoon, there I'm in November Platoon. I just want to see if this works. I don't know why it didn't work. So if I do create table students, ID, serial, I'm just going to primary key, first name, varchar 255, not null, last name, varchar 255, not null. There we go. So before I accidentally forgot that part. So I literally can either execute that file like I did before, or literally do a query to create the table. So I can do \D that shows all the list of tables. So if I wanted to create another table like addresses, I could do that as well, but I don't want to do that right now. Cute. So I'm going to clear that. So if I wanted to add some data into this, so again, I'm back in my November Platoon database right here. If I wanted to add data into it, I could do like insert into what is it? Students. And I can do first name, comma, last name to students. Let's look at, I think it's values. So values. Let's just say Tom, last name Preet. And then always don't forget to put that closing semicolon. So now we get insert 0, 1, so 0 to 1. Now I can clear it. Whoop. Didn't mean to do that. So November platoon. Now I can also do, so I inserted a user in there. I'm gonna clear it, clear the screen, go back into it, give some more real estate. So just, I can do \D, that will have a list of tables. And I can also do \D, the name of the table. So I can see the list of tables. Now I want to grab that students table and do that. And I can see the different types, the field types. So like ID integer right here, ID is an integer. Last name is a character varying to 255, not null. Last name, exactly, different. So you can actually inspect the different tables as well. Clear, just to give you some space. So I inserted into the students table. Now I want to query to grab all the students. Select star from students, the students table. And now I get ID, first name, last name, Tom Preet. All right. I'm going to quit. I'm going to use a different database that already has a little more data in it. PSQL November. So I also have a database called November in it. So I got November. And in here, if I want to select everything from students, I get all these users in here. So first name, last name, I got Tom Preet, Ruthie Cohen, John Doe, Joan Greenwood, Cosmo Kramer. Now, if I wanted to select all the users or select the user with an ID of 4, so I can say select star from students. So select every student or select everything that's star from the students table where the ID equals 4. And now I get Joan Greenwood. So Joan Greenwood's up here. Now I only have Joan Greenwood down there. So I'm only selecting that individual. Now I can also select all the students between 2 characters as well. Let's see how I do that. So I can say select star from students where ID, I forgot how to do that one. Where is it? So I forgot how to do it between, not BWE, between SQL. Between SQL query. So I looked at this in the past. So it looks like right here, select column name from the table name where column name between 2 values. Cool. So let's look at that one more time. Select column name. So I'm selecting everything. For example, maybe I want to select just the ID and first name. ID first name from the students table where column name, where ID between, so first name, last name, where ID is between 3, so let's say 2 and 4. So there we go. We got all the users between IDs 2 and 4. So Ruthie, John, Joan, and we're only grabbing their ID and first name. Cool. Maybe I wanted to grab, I'm just gonna clear it. Go back in there. So maybe I wanted to grab all the users that have a first name that starts with a J. So I can do select, I'm going to just the first name students. Select first name from students, the students table, where first name, like, and then I'm going to do, that has a J in it. So I can do wildcard, J wildcard. So this means anything before it, anything after it. So it doesn't matter what characters are before it. This doesn't matter what characters are after it. So if I wanted to just have it start with a J, I can do J. And if I do that, Joe and John. If I wanted to do this also would probably return the same thing, just because there's not another first name that has, but this essentially says anywhere that has any user that has a J in their entire name. Now, if I wanted to do a J, an ending, so any people that have, actually, let's do any user that has a first name that ends with an M. So this says ending with an M, it doesn't matter what comes before the M. Like so. So Tom is the only one. Or if I wanted to say that has an O in their name. So we got Tom, Joan, John, Cosmo. Clear, quit, clear. And you can also run these queries in a file. So if I wanted to create a file, touch queries.sql. Now I've got a queries file, and I want to say like, hey, select star from students, and save that. And I want to run this file on the November Platoon database. I can do PSQL November insert, so angle bracket, the queries file. And that query runs, and it outputs whatever's returned from the database. I can even run it on the November Platoon, which only has one user in it. Cool. All right. With that, that concludes our intro to SQL.